Hello and welcome to the second part of our lecture on compensating wage differentials. So if you recall, in our previous lecture we talked about a trade-off between safety and wages for both the firm and workers. In terms of the firm, increasing safety is costly, right? In order to keep their profits constant, they would need to lower the wage to offset any higher costs associated with increasing their safety. And we characterize this trade-off using the ISO profit line. For the workers, and of course for firms, we're assuming a competitive market, so the ISO profit curve, it has zero economic profit. Now for a worker, we characterize this trade-off with the indifference curves. Lower safety to a worker means they need higher wages to compensate, and vice versa. And in a competitive market, we would have an offer curve. So if there's different firms, different types of firms, so if you remember, we're assuming that firms have different technology in which to offer safety. And so the more firms there are, the more heterogeneity, the more differences, the more smooth this offer curve would be. And if you remember, it's always going to slope downwards, because there's a negative trade-off between wages and safety. It's based on our assumption that that risk is costly to reduce and that employees must be paid higher wages to keep their utility constant. And so our model would suggest that there would be a sorting of workers and firms, so there'd be this mismatching or matching going on between employers and employees, and the market would then determine a wage safety locus, or sometimes called the hedonic wage function. And this is telling you in the competitive market what the change in wage with respect to a change in safety would be. And so if you remember, workers are going to have different preferences, firms have different technologies for what they can offer in terms of wages and safety, and there's going to be people who are less risk adverse. So there's going to be people who don't mind being exposed to a higher level of risk if they get paid more, but some people are very risk adverse. They would rather have, forego higher wages for higher level of safety. And so there's going to be compensating wage differentials for job characteristics that are viewed as undesirable by workers. And we see that we're going to have overall this matching of employer and employees. And so this was the model we learned last class. Now we're going to apply it to see the effects or impacts of a safety standard. So let's suppose we have a worker in a firm, and the worker would optimize by choosing this point here. So they would accept this wage for this level of safety, and this would maximize their utility. Now, what if the government comes along and forces the firm to have a level of safety of SR? Okay, is that, what's the impact of that? Is the worker going to be better off or worse off? Well, the worker is definitely going to be safer now, but does that mean they're going to be better off? Well, we know that in our model, which is quite realistic, we assume that workers not only get utility from the wages, but they also get utility from safety and also wages. And so this person here was not willing to choose SR on their own. So of course, if they're forced to take SR, they're going to be at a lower level of utility, and that would be associated with this, or correspond to this indifference curve UR. So if the government came along, forced the company to only provide this, at least this level of safety, the worker would be made better off. This worker would rather be exposed to some risk in return for this much higher wage. They'd be happier here than here. Okay, so in this diagram here, we're assuming that the firm is on its zero ISO profit curve, and that the worker then would just be forced to be at this level of safety. Though we're assuming here that the firm would have to lower their wage by this amount to keep their profits constant, and there would be zero profit. So this is the zero profit constraint. And so here the worker is going to be taking all of the burden of this safety regulation. But of course, in reality, this may not be the case. If, for example, a firm was able to actually have some excess profits, so suppose that the isoprofit curve isn't the zero isoprofit curve and they actually have some profits here, then they could keep the worker equally happy, and they would do this by, so this is the original indifference curve, okay? So if they wanted to keep the worker equally happy with the safety regulation, they would have to offer them a higher wage. And then that higher wage would correspond to a higher isoprofit curve. And if you remember, that means that profits are lower. Profits decrease as isoprofit curves move in the northeast direction. Let's just compare and contrast the last diagram so we understand this. So in this situation, the worker is going to be worse off because of the safety regulation. But if the firm paid them a wage here, okay, and that's what we're depicting here, that's on the same indifference curve as before, then the worker wouldn't be worse off. It would be the firm that's worse off. And you could think potentially in the real world there could be some room for negotiation between the firm and the worker, but that's only if the firm is able to have not zero profits. So the firm would go out of business if they couldn't get any workers to work at the lower wage associated with that new safety regulation. So let's think about the response or the impact of a safety regulation in terms of the firms, because not all firms might be able to meet that safety regulation. So let's look at an example here. So we have firm 1. Firm 1's isoprofit curve is like this. Clearly we see that as we increase safety, this firm, it's very expensive for them to increase safety. If they go a little amount, they have to drop the wage. So you can see the wage having to drop a lot here for increases in safety. But firm 3, they can provide safety much cheaper. They don't need as much of a drop in the wage. Okay, so these are quite different. And then the firm 2 is sort of in the middle. So this would be the offer curve in the market. Now, if the government came along and said the safety cannot fall below SR, what's going to happen to the different firms? So for firm 3, no problem. Okay, they can offer these wages here and these safety levels, so they have no problem meeting the safety regulation. Firm 2, it can meet the standard only if workers accept wage cuts. Okay, so if it had some workers here, they would need to accept wage cuts to be, at least on this portion here. And guess what's going to happen to firm 1? Well, firm 1 is going to go out of business. They can't meet that safety regulation. They would not be able to be profitable. If this is their zero profit isoprofit curve, which we're assuming it is, then the only way they could meet the safety regulation is by being on a higher isoprofit curve, and that would mean they'd have negative profits. And so they would go out of business. So the bottom line is the one positive aspect apparently of a safety regulation would be that it would weed out firms that cannot provide safe work environments, like in the previous example, the firm 1. However, the workers now, are going to be forced to give up wages for extra safety, and that may not make them better off. Without government intervention, workers were choosing the wage and safety combination that maximizes their utility. With the safety standard imposed, they now receive a lower wage and hence lower utility in the safer jobs. Now, up to this point, we've assumed that the firms can't trick the employees into thinking the work environment is really safe when it is in fact not. So we're going to relax that assumption and look at an example where perhaps the worker is misperceiving their utility and their level of safety. And we'll see there's actually room for a safety regulation in this sense, in this case, to actually increase the utility of workers. And it could lead to a more optimal amount of safety. So let's take a look. So we have our model. We have an isoprofit curve. We have a worker whose optimum would be at E0. Okay, so this is the case of perfect information. So we're going to assume perfect information here. Now, what would happen if the worker actually was wrong? And let's suppose that the worker was being paid W actual, and they perceived their level of safety as SP. But in fact, their safety level was SA. Okay, so their real safety level is SA. So their actual utility then would be here. They're being paid this wage, but only being provided this level of safety. So this would be their real utility. And so what's interesting here is if the government were to enforce a safety regulation anywhere in between SA and SR, they would actually make the worker better off. So the worker is right here. This is their level of utility. If the worker accepts any wage or safety combination on this line anywhere, their utility is going to be higher. Okay, so anywhere in this range, they would, so any safety regulation that the government would oppose between SA and SR would actually make them better off. Okay, and think about where the optimum would be. The optimum would be at E0. If the government could, if they had perfect information and could properly determine what safety level this firm should offer, it would be S0. If the government offered a safety level of S0, then the worker would be at their optimum. Okay, so in a nutshell, a safety regulation could improve worker utility if there was imperfect information and the worker was perceiving the level of safety to be a lot higher than it actually is. So again, mandated safety levels between SA and SR would make the worker better off because they would be able to reach a higher level of utility. Another example would be, say, SX. If the government decided to mandate SX, then the worker then would be here. The firm would offer this wage and safety combination. Well, they'd have to offer this safety combination. And so then the worker would be at a higher indifference curve. Okay, so again, all the safety levels between SA and SR, any of these, if they were mandated in this situation, would improve the utility of the worker. So the rationale for regulation is, actually this example provides some rationale for regulation. We first saw that it would only make workers worse off, but that's in the case of perfect information. And so in the real world, information is not always perfect. And so this gives some motivation for actually having a regulation, because it could, as we just saw, there are situations where they could improve their utility. Also, the market may not be competitive, so workers may not actually have a choice. There may not be enough firms. And it's important to realize that the worker doesn't always bear all the cost of an accident. So it's not just the, so if a worker is not very risk adverse, they like to take on risk to get that very high wage. Well, it's not just them that they're going to affect if there is an injury. It's also the government, which has to pay for the health care associated with that. So that's another reason to have regulation. And just, a social opinion. Maybe many people believe that, although people don't, there are people that would like to, would not care about being exposed to very high levels of risk because they get a very high wage. We shouldn't allow them to do that as a society. So let's talk about calculating the value of life. So we can actually use some of the ideas here to be able to tease out some numbers to get the value of a human life by looking at correlations between the probability of injury on the job and the wage. So let's look at an example. So suppose we have firm X, the probability of fatal injury is rho X, and annual earnings are WX. And firm Y, the probability of injury is 0.001 higher, and their wages are $5,000 higher. So in this case, the difference in earnings between the firms is $5,000, and the probability of fatal injury is 0.001. Okay, so that's for every 1,000 workers, there would be one injury. So the data suggests here that each worker in firm X would be willing to give up $5,000 per year to reduce the probability of fatal injury in their job by 0.001 units. Okay, so if we just take this and multiply it by 1,000, we know that'll equal 1. So if we take 1,000 and multiply it by 5,000, that would be for one life, and so that would be $5 million. So to calculate the value of life, we assume we have wages in the two different firms. We have the probabilities of injury in each firm. And then to calculate the value of a human life, you're just looking at the change in wage, the difference in the wage. And we look at, we're assuming Y is the risky firm, X is the non-risky firm. So this should be higher than that, and this should be higher than that. And these are the differences in the probability of injuring. So when we calculate this, we would get the value of a human life. So in the previous example, we would get 5,000 over 0.001, and we'd end up with $5 million. Another way of thinking about it is, suppose that each firm has 1,000 workers. Well, so if we take 0.001 and multiply it by 1,000, that means one worker in the firm will die. Okay? So put differently, the 1,000 workers employed in firm X are willing to give up $5 million. Okay, so there's 1,000 workers times 5,000 to save the life of one worker who will almost surely die in any given year. And so the value of a human life would be $5 million. And sometimes this is also called the statistical value of a life. So there's been a lot of research done on this. So typically regressions would be run of the following form. So we have wage as a dependent variable. As an independent variable, we have the probability of injury, and then we have this gamma coefficient in front. And so this here would measure the change in wage with respect to a change in the probability of injury. We also have some control variables. And so if we were to estimate this, the gamma would give us the change in wage over the change in probability of injury, and that would be giving us the value of a human life. So there are some studies that have looked at this. There's actually quite a few. Typically, they find that there is a positive relationship, which we would expect. So there's a positive relationship between wages and work hazards. A study by Gunderson and Hyatt in 2001 found that the estimate for Ontario in Canada was roughly 2.8 million. Some authors, Cooper, Hammett, and Robinson in 2011, actually did a literature review in the US and found that the estimates range is quite large, from $2 million to $11 million in 2009 dollars. So it's not it's difficult to get a very precise estimate, but bottom line is there are ways of teasing these statistics out of the data. Okay, let's do some practice questions. Consider a competitive economy that has 4 different jobs that vary by their wage and risk level. Okay, so we have 4 different jobs. We have different risk levels. So 1 divided by 5, 1 divided by 4, 1 divided by 3, 1 divided by 2. So the highest risk job here would be D, because the probability or risk is half, 0.05, and we see that the wages increase with this higher level of risk. Now let's suppose all the workers are equal, but workers vary in their preferences. Consider a worker who values his wage and risk level according to the following utility function. So utility is equal to the wage plus 1 over the risk squared. Okay, so the first question is, where does this worker choose to work? Okay, so where would a worker choose to work? And then B, we're asked, suppose that the government regulates the workplace and requires that all jobs should have a risk factor of 1/5. That is, all jobs become A jobs. What wage would the worker now need to earn in the A job to be equally happy following the regulation? Okay, so the first question, where does the worker choose to work? Well, we arrive at that answer simply by plugging in the different risk levels into this utility function and finding the highest value. When we do that, we get 28, 28, 32, and 29. So this individual will choose job C because it provides them with the highest level of utility. Now, if the government were to regulate all the jobs to be like A, then this individual, in order for them to get the same level of utility, they would have to be paid a wage of $7. So all we're doing to get that is taking what the utility they would get in job C, which is 32, and setting that equal to the utility function with the 25 in there. This is the 1 over the risk associated with job A squared. And then we're just, our variable to solve that equates this is W. And so when we solve for that, we get 7. Okay, next question. Suppose a labor economist estimates the following regression relating annual earnings to the risk of on-the-job death in the workers' industry. So we have earnings. This is similar to what we looked at before. So we have our wages or earnings as a dependent variable, intercept term, plus a coefficient in front of the risk variable. This risk variable here is the death rate per 10,000 workers. Okay, when the researcher does the estimation, she obtains a statistically significant coefficient of beta hat equals negative 30.03. So is this coefficient correct? Okay, so that's the first question, is to interpret this, and is it consistent with theory? Okay, well, let's think about this. This is saying that a 1 unit increase in risk results in a fall in earnings of 30.03. Okay, so the problem here is that it's a negative relationship. So we're not very, this estimate is not really consistent with theory. The thing is, the theory states that this should be we want to hold other things constant, other important determinants. So in this regression, we haven't controlled for everything. Okay, so it's not that surprising that the estimate doesn't make any sense. So in a second attempt, the labor economist adds other control variables to the regression, such as the worker's age, education, union status, occupation. So important controls that we would want to have in there as well. So we want to hold other things constant, like age, education, union status, etc. When we do that, we get an estimate of 43 positive 43.10. And so now is this, let's interpret this and let's calculate the implied value of a human life. Well, here we have that a 1 unit increase in the risk level increases earnings by 43.10. Now, these earnings are actually in tens of thousands of dollars, so keep that in mind. So the answer to A we already went through. We need a ceteris paribus relationship. We didn't have that because we weren't adding any control variables. So this coefficient is likely biased. So now we're going to estimate it again with control variables, and we end up getting that the coefficient estimate is 43.1, and it's positive. Okay, so this coefficient would imply that as the death rate increases by 10,000 workers per year, annual earnings increases by 43.1. So if you remember before, the value of a human life is the change in the wage divided by the change in the probabilities of injury, okay? And then we know that's the coefficient. We know that that's 43.1. So if you recall, the value of a human life we can calculate by looking at the difference in wages with respect to the difference in the probability of risk, holding other things constant. And here we estimate that to be 43.1, but since earnings are in tens of thousands of dollars, we multiply that by 10,000, and we get that the value of a human life would be worth 431,000 according to these estimates. Okay, let's do some multiple choice questions. So, risk adverse workers, finish the sentence. A, have shallow wage risk indifference curves when risk is graphed on the x-axis, are willing to work in riskier environments for relatively low increase in the wage, are willing to accept large wage decreases in exchange for safer work environment. I think C is the answer. This is clearly, we can, if you remember when we looked at the different indifference curves, someone who's risk adverse, if you take away some of their safety, they're going to want a much higher wage to compensate for that. So they have steep indifference curves. So they, and so the other side of the coin of that is that if you give them a little bit of safety, they would accept larger wage decreases to keep them equally happy. Okay, so the answer here is C. Next question. Which of the following is not a property of isoprofit curves graphed in safety versus wage space? Okay, so what is not a property of an isoprofit curve? So I'll let you take a look. You might want to pause it, think about what the correct answer is. Okay, so C is the correct answer. Isoprofit curves moving in the northeast direction depict higher profits. That's incorrect. That's not a property. Okay, the rest of these are true. Now refer to this diagram. So in this diagram we have three different indifference curves. We have different safety levels, we have different wages, and it says here, refer to the figure on the left and assume that the worker perceives their level of job safety as S4 up here and accept a wage of W1. What is the worker's actual level of utility and level of safety exposure? Okay, so we know that the wage offered must be on the isoprofit curve, and so that's going to be right here. Okay, so their actual wage is W1 and their safety level is S3. Okay, so the answer is D. And so they would be on this indifference curve, getting wage W1, so U3 and S3. Okay, we have the same diagram. Now it's asking us to, it's asking us what the range of safety levels that, if imposed by the government, would increase the worker's utility. So remember, we learned about this. We learned that if there's imperfect information, there's a certain range that would increase the worker's utility, and that range is between what their actual level of safety is up to this point here, which would be at S5. So we're looking for this sort of oval type shape, or this envelope, I guess you could call it. We're looking for this thing here. We know this is the safety level, so any safety level above this would give them higher utility on the, as long as they're getting the wage on the isoprofit curve. So this is what wages the firm would offer for different levels of safety. Above, so this area here would be all wages that the firm would offer for safety levels between S3 and S5. And all of these, if the worker got them, so any of these wage and safety combinations would result in a higher level of utility. Okay? So here the answer is S3 to S5. So it's C. Okay? So now look at this question. Refer to the figure on the left and assume that the worker is maximizing their utility and working for wage W2 and facing a level of safety of S4. So W2, S4. If the government imposed a safety regulation of S7, which is here, the worker's level of utility will now be what? Will it be what it was before, U4? Well, no. Now this person is forced to work in this safety environment, but they're only going to be getting a wage on the isoprofit curve of this. So they're going to be at this point here, and this point here is associated with a lower level of utility, U2. Okay, so the answer here is B. The worker would be worse off. Okay, which of the following is correct? In a competitive market, imposing safety regulations is easy since all firms will adopt it right away due to the market competition. Well, that might not entirely be true because of firms not being able to, they have different technology. Some firms may actually go out of business. In a competitive market, a legislated increase in safety will make people better off. Well, we know that that's not true because we saw that in many cases, at least especially in the case of perfect information, that it could make them worse off. In a competitive market, the application of a uniform safety standard will weed out the firms whose safety technology is not sufficient to meet the standard. Yes, that's the correct answer here, and we looked at that example on one of the slides. So there could be certain safety regulations that are too high for some firms, and then it would weed them out and they would go out of business. So the answer is C. Okay, well, thank you for listening. This is the end of our lecture. Our next lecture will be on the human capital model, and we will see you then. Thank you and have a great day. Bye.